Okay, so we just finished the problem with the cannonball being shot across the field, and there is a formula in the book that will help you only if you're on a level elevation. So if you're on a flat field, a soccer field, a football field, then there is a formula in the book that deals with level elevations, and it's called the range formula that can only be used in that one case. So let me write that down. Okay, so it's called the level elevation range formula. The book calls it the level horizontal range, and this is the way it is written in the book. It says this: R for range equals V initial, which we're going to square that, times the sine of 2 times the angle, divided by, and in this case they have G. Now G really hasn't been explained yet, but I'll just put it here as G. G is the magnitude of the acceleration due to gravity. So G is going to be the number 9.8. Okay. It's the magnitude. Okay. So with this particular formula, the range is equal to V initial, which gets squared, times the sine of 2 times the angle, and G here is the magnitude of gravity. The V initial from the last problem, V initial was 60 meters per second. We said the angle in the last problem was 35 degrees. So with those two things there, I can just plug in this thing called the range formula and see what I get. So if I plug it in, it would be 60 meters per second. I'm going to square that, times the sine of 2 times, and I'm going to times the angle, that's 35 degrees, divided by the number 9.8. Okay. So if I just plug those into my calculator, I'm going to take 60 squared is 3,600. We're multiplying it by the sine of 70 degrees, because that's 2 times the angle. You have to do that piece first, and then we divide it by 9.8. And this answer comes out to be 345.19 meters. And that's the range. And the range is the same exact thing as delta x. So this is a fancy way of saying delta x. If you look back through the video we just did, you'll see that this number is very, very close to the last number we did. It might be different by a few decimal points or something. Okay. So far, everything we've done, we've been able to use the old formulas we learned in Chapter 2 and keep everything separate with the x and the y components. But this one formula is useful if they don't give us the angle at the beginning and they ask us to find the angle. So you see, what if they did say something like this? What if they said that a cannon So in this particular case, I'm saying that we have a cannon, and the cannon's going to launch these cannonballs with a speed of 60 meters per second. Then I'm saying that the cannonball will travel 300 meters across the field, a flat field, when it lands. And then I'm saying find the launch angle. So for this particular case, the range formula is perfect. So if we use the range formula, what it says is range equals V initial squared times, well, V initial square that, times the sine of 2 times the angle, divided by the magnitude of gravity. So you see, I know a few of these things. I know the range is 300 meters. I know the beginning speed is 60 meters per second. I'm going to square that. I know the sine has a function of 2 times the angle. Now I don't know the angle, and I'm going to divide this thing by 9.8. So if I go and I try to solve this, what I will get is I'll do just these pieces right here. So I'm going to get 300 equals, so let me do 60 squared, which is 3,600, and divide it by 9.8. It comes out to be a number on my calculator, 367.35. So it's 367.35, and that's the only thing that's left is meters there, times the sine of 2 times the angle. So if I take 300 meters divided by 367.35 meters equals the sine of 2 times the angle, then I have to do that division. And this here comes out to be a lot of decimal points. I would keep at least 4 numbers after the decimal point. This is 0.81665, 0.8167, I'll say. And that equals the sine of 2 times the angle. So now I'll go for this and I'll take the inverse sine. So if I say sine minus 1 of 0.8167 equals, well, I take the inverse sine of the sine. When you take the inverse sine of the sine, it just disappears and you'll have 2 times the angle. So if I do this on my calculator, it's 54.75 degrees. And that equals 2 times the angle. So if I divide both sides by 2, you get 27.37 degrees. So from our calculation, we just calculated that the angle should be 27.37 degrees, which is right here. So according to the formula we did, if you launch a cannonball at a speed of 60 meters per second, it should go across the sky following a parabolic path, and it should land over here, which is a distance of 300 meters away. And that's what we just found a moment ago. The thing I haven't said yet is any 2 complementary angles will do the exact same thing. So, okay, so what did I write here? I wrote any 2 complementary angles will give us the exact same result. So they'll give us the same range. So what is a complementary angle? A complementary angle is when you take 2 angles and add them up together and you get 90. So if I know one of these angles is going to be 27.37, the complementary angle would be, let's say, theta 2. So if I wrote 27.37 degrees plus angle 2 equals 90, well, I just have to take my calculator and subtract those two. And if I subtract them, I'll get this angle 2 could be 62.63. Okay, so 62.63 will also land at the same place. If I were to launch this thing at a 62.63 degree angle, it would be going up much more steeply. So if I launch it at a 62 degree angle, it still has the same speed of 60 meters per second, but now that angle right there would be 62.63 degrees. And what would happen with that one is it would just go up. It's going to go up the screen, and it would go way, way up, and then later it would be coming way back down, but should hit at the exact same spot. So any 2 complementary angles will always land at the same spot. If you remember, one of the first examples I did with this exact same problem is I said we were going to launch this cannonball at a 35 degree angle. So if I were to launch it at a 35 degree angle, and we did that just about 2 problems ago, same exact thing. If I launch this one at a 35 degree angle, 35 we said would land at 345. So this drawing is getting a little bit messy. So earlier I said if you launch it at 35, so if I would launch this thing here at a 35 degree angle, and that's still the cannonball, so it's still going at 60 meters per second, we said that it was going to go 345 meters. So it's going to land way over there, which is a little bit further away. That's going to land at 345 meters, we said yesterday. Well, what's the complementary angle to 35 degrees? 35 degrees. Take 35, add some unknown angle to it, and it equals 90. So 35 plus 55 is the answer, equals 90. So if I launch this thing at 55 degrees, then that there would be 55 degrees. If I launch it there, it's going to go up, 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 up. It's going to go much further up in the air. It'll be up in the air longer. And it's going to come back down, and it's going to hit at exactly the same spot. If you remember yesterday when we did this, this was hitting at approximately 345 meters away. So that was the entire range for that one. So with projectile motion, we can do almost all the problems with just the 4 formulas of constant acceleration, which we have learned in Chapter 2, but there are some cases where additional formulas might be useful to use. Before I leave this piece, I just wanted to say, based on these 2 different complementary angles, the furthest one will be if we launch something at an angle of 45 degrees, that's the furthest it can ever go. So what I'm saying here is if you launch something with an angle of 45 degrees, that is going to give us the largest value for the range that we'll ever get. So any other value, we're pretending there's no air resistance at all, and any other value will give you a much smaller number. Okay, so now I have a problem, and the problem has this Stomp rocket idea. And a Stomp rocket is a children's toy, a child's toy. So what it is it's a little rocket, and it's filled up. It has a little pouch that's filled up with air. It's a little plastic pouch, and that plastic pouch is attached to a tube where the rocket sits on. So a child would go and take their foot and stamp on the rocket, and they stamp their foot on the pouch. All the air gets squeezed out of the pouch through a tube, and the tube then the air gets squished through the tube, which launches the rocket. It's the air that's pushing the rocket up. So this kid's toy says that the Stomp rocket is going to launch at a speed of 10 meters per second. So we've got the initial velocity, and it's going to land 8 meters away. So we've got our range, and they're asking at what angle or angles, 2 angles, might this thing be launched at. So we'll use the range formula. So the range formula can only be used if it's on flat ground, and this, they didn't talk about a different elevation, so this will be on flat ground. So we're saying that the range is equal to the initial velocity squared times the sine of 2 times the angle divided by gravity. I'll plug it in. The range is 8 meters away. The initial velocity is 10 meters per second. We have to square that. It's times the sine of 2 times the angle. And we're going to divide that whole thing by the magnitude of gravity is 9.8. So if I just do this math right here for a moment, I'm going to get 8 meters is going to equal, now let me do that piece on my calculator. And that comes out to be 10.2 meters times the sine of 2 times the angle. Okay. So now what I can do is I can say, let me get the angle by itself. Some lines there. So if I get the angle by itself, I'll divide both sides, but so it's 8 meters over here, divided by 10.2 meters, equals the sine of 2 times the angle. Okay. So I want to get the angle by itself, but it has this sine function in front of it, so I have to do the opposite. So why don't I move up here and say, take the opposite function. So the sine minus 1 of 8 meters over 10.2 meters equals the sine minus 1 of sine, the inverse function of sine, inverse sine of sine, cancels out, and you're just left with 2 times the angle. So let me do this piece on my calculator. So this is going to be the sine minus 1, and the decimal points are 0.7843. And that equals 2 times the angle. So when I take the inverse sine function, and I have to be in degree mode, it's 51.65. So if I want to get the angle, I divide both sides here by 2. So the angle would end up being just whatever that is divided by 2, 25.82. Okay. So that's one of the angles. So if you had this toy and you stomp on the pouch with air and the rocket launches at 10 meters per second, if it's set up like this at 25.8 degrees, it's going to land 8 meters away from you. But there's another angle, because the question said find the angle or angles. So there's another angle that will do this also. And that other angle would be the complementary angle. So how do we get the complementary angle? Well, this is angle 1. We can get angle 2 by saying take 90 degrees and minus 25.82 degrees. So if I do that, it comes out to be 64.18. So 64.18 degrees can be angle 2. Okay, so that's what happens here. And if you don't believe both of these things can be angles that will end up giving you the exact same range, plug it into the original formula. The original formula is right here. So they both will launch at a speed of 10 meters per second. They both have gravity effect of them, negative 9.8. There's two different angles. Plug the two different angles, do the formula twice, plug the two different angles in, and you will see that that's how it lands.